طيب السلام عليكم everyone.
وعليكم السلام ورحمة الله.
عليكم السلام.
وعليكم السلام
وعليكم السلام ورحمة الله. أهلا وسهلا.
طيب, we started this subject last time. Do you have any question before we start our lecture? Because we are behind material, so I will try to accelerate a little bit and cover the material as soon as I can before the exam, which is next week, Tuesday. So do you have any question before I start explaining the material today?
دكتور ممكن تنزل السلايدات هذه بدري؟
I will try to do it inshallah either today or tomorrow. As I said, the problem is that I need to revise the slides and make sure that this is what I need you to have. I don't want to post a few slides and after that keep updating, or post slides and after that remove them and post them again. يعني بالعادة الطلاب شوي يتلخبطون. Just to avoid this, I want to make sure that this is 100% correct, and after that I post them to you. Okay? So
طيب
inshallah
معلش يعني معلش يعني ممكن شوية تبكر على أساس نلحق برضو حتى احنا نذاكر بدري يعني، لأن ما أدري ما أشوف أنا في سورسز يعني ثانية على أساس نذاكر منها.
الكتاب المفروض انه يصير جاهز اونلاين لكم خلال هاليومين على حسب ما اعطونا خبر. فاعتقد انه بيرسلون لكم ايميل على هالموضوع، وان شاء الله مثل ما قلت لكم قبل الويكند اني احط لكم سلايدز
إن شاء الله.
Okay.
إن شاء الله.
So we'll continue our subject, and if you remember last class we discussed this power system, and I mentioned that the whole power system is working on a three-phase. It means that we generate a three-phase power or voltages and currents, we transmit three phases and also distribute three phases. So today we're going to talk about what do we mean by three phases. So by now we should know exactly what is the power grid, the main components, subsystems, how the power grid is operated. And now we're going to talk about the three-phase systems. Before we go to the three phases, let's talk a little bit about the single phase, which is basically how we generate single phase. We generate single phase, and when we say single phase, first of all, it's AC, so it's this basically sinusoidal function that you see in figure 1. We have frequency, we have duration, cycle duration, and we know that the frequency in the kingdom is 60 Hertz, means that we have 60 cycles per second. In other countries we have 50. So single phase, or the voltage single phase, or the current single phase, it's one sinusoidal function with 60 Hertz frequency. That's it. This is the single phase voltage, for example. We have magnitude, we have frequency, and this is the time domain. And if you attended basically the help session yesterday, you know that we can also represent the voltage using the magnitude and the angle, which is called the polar form or exponential form. So this is basically the single phase. How we generate this? Well, we generate this from the generation side. So we use a generator that can generate only single phase. And we are going to study about generators later in this course. The basic concept of generating the voltage using generators is that we have what we call armature coil. The coil is basically a bunch of wires wrapped around magnetic core. Again, don't worry if you don't understand this now, because we'll explain it more in the coming few weeks. So if you have a magnetic field and you have wires, and if you remember from physics 102, voltage will be induced in a wire if it passes through a magnetic field. That's it. So it means that if you have magnetic field and you have a wire, and this wire is moving in the magnetic field, or the magnetic field is moving on the wire, around the wire, voltage will be induced, which is the basic concept of generating electricity. This is how we generate voltage. This is how we induce voltage. Okay? But instead of wire, we don't use wire, we use what we call winding or coils. And this is how we can get similar sinusoidal function. How we can get the frequency? How we can get 60 or 50? Well, it depends on the speed of rotation. So if this magnetic field is rotating because of the shaft of the mechanical rotation, well, if you increase the speed more, the voltage induced in the wire will have more frequency or higher frequency. Makes sense. The question now is how we can generate 3 phases, not only single phase. Well, this is how we can generate 3 phases. Well, we have magnetic field, which is this source, and it is rotating. It rotates with this specific mechanical speed. And we have here what we call winding A, winding B, winding C. So at certain point, the voltage will be maximum at A. And let's assume that this is this point here. We are showing the currents, but it's applied also for voltages. When this basically rotates, what will happen is that at another point, the maximum voltage will be induced at B, which is this point. Later, the maximum voltage will be induced at C, which is this point. So when we complete one full mechanical rotation, what will happen? We are basically getting 3 different voltages, A, B, and C, induced in the 3 windings. So in one full magnetic field rotation or one mechanical rotation, we are inducing 3 cycles of voltages, not only one. Makes sense, right? And all the voltages will be sinusoidal. Why? Because it is moving. So the magnetic field will be maximum, but it will move later to another point. Now it will be different here at A. It will be minimum maybe. So that's why we have this shape like this, which is sinusoidal function. So this is how we generate 3 phases of voltages in the same machine. What are the characteristics of these 3 voltages? Well, first of all, they have the same electrical frequency. Do you agree? Yes, because all of them, they are generated from the same mechanical rotation. So the same frequency. All of them, they have the same magnitude. So if the maximum here is 100, the maximum here is 100, the maximum here is 100. Does this make sense to you? Yes, because all of them, they are exposed to the same magnetic field. The main difference between them, so we said that they have the same frequency, the same magnitude. So what's the difference between them?
The angle.
The angle, the phase shift, good. And it does make sense again. Why? Because they are separated inside the machine. The difference between any 2 phases is actually 120. So this angle here is 120. And this is like the mechanical angle actually, not only the electrical angle. So all the 3 phases, all the 3 windings that you see here, they are separated by 120 degrees. So at 0, for example, when you start the machine, let's assume that you are starting the machine and you are getting the maximum voltage at A, and the angle or the reference at A is 0. After 120 degrees, the maximum will be at B. After another 120 degrees, the maximum at C. Or you can say that with minus 120, the maximum at C. So again, to summarize, three-phase system, it means that we have three signals, three voltages, have the same magnitude with a phase shift of 120 degrees between them. Do you have any question regarding this?
Doctor?
So my question is, if we want to generate actually 4 phases, what should we do?
The angle will be different. Should we divide the 360 by 4?
Yes, but how many windings we are gonna use here?
4 winding.
4, and the angle will be 90, right? Makes sense. 2 phases, we will use 2 windings, and the angle will be 180. So hopefully it's clear now. Is it clear why they have the same magnitude? Why they have the same frequency?
Yes.
Because all of them, they induce the voltage using the same magnetic field inside the machine, which we are gonna talk about more inshallah in the coming few weeks. So this is mathematical representation for the 3 phases that we are talking about, and you can see the signals here and the phase shift, which is 120 degrees. The phase A, the angle, usually the reference is at A, so the angle here is 0. The phase B, minus 120 degrees. Phase C, minus 240 degrees. Okay, and we're gonna see the different sequences that we can get for the 3-phase system. So this is the mathematical representation. We can use the exponential or the polar form. By doing this, the phase A will be the magnitude and the angle 0. Phase B will be the magnitude and the angle minus 120. And phase C will be the magnitude and 120 degrees. And again, as I mentioned, the magnitudes will be the same for the 3 phases. And this is the phasor representation where we have the phase A with the angle 0, phase B with the minus 120 degrees, and phase C with either 120 or minus 240. This is called the positive sequence. And there is another sequence which is called the negative sequence that we are going to talk about later. So the positive sequence is when we have A at 0, B at minus 120, and C minus 240. And you can imagine this as like a rotation of these 3 phases. Okay? A comes first, then B, then C. It's like you are rotating counterclockwise all of these arrows, and the sequence will be A, B, C. Okay? Again, if you remember from the discussion yesterday, we don't use usually the maximum value or the peak. We use the RMS value, and the way to change from the peak to RMS value is by dividing the peak by square root of t. The square root of 2, sorry. And usually values, they are given in RMS value, unless it's given in time domain, which is peak value, or it is mentioned that this is a peak value, not RMS value. As I mentioned, we have 2 sequences for the 3 phases. By default, it's positive sequence, meaning that we have A, B, C. So if I ask you write the angles for the positive sequence, you'll say that A is 0, B is minus 120, C is 120. If I don't mention what's the sequence for the three-phase system that you are dealing with, by default, you should assume that it's positive sequence. The other sequence is called the negative sequence, or ACB. So for ACB, you can notice that A is still the reference, but then we have C, then we have B. So if I ask you to find or to write the angles, you'll say that A is 0, C is minus 120, and B is plus 120. Any questions so far?
دكتور
Mm-hmm.
معلش ممكن تعيد اللي البوزيتيف كيف بيكون السيكونس حقها؟
Okay, for positive sequence, it's ABC.
تمام.
So the voltage of A will be the magnitude and the angle 0. Voltage of B will be the same magnitude, but the angle now minus 120. C, V, 120.
تمام.
For the negative sequence, you change from these two angles.
Yes.
C will be minus 120 and B will be 120. As I said, in phasor representation, imagine this, it's like this one is rotating counterclockwise. So if you are standing here, you will see A, but after that with rotation, what's the next one? B. And after that C. You get my point?
Yes. I got your point.
Okay. So the next subject is basically how we can connect the three-phase system. We know that we generate a three-phase system, we transmit a three-phase system, and distribute a three-phase system. But before that, let's discuss how we do it for single phase. So let's assume that we have one single phase and one load. Imagine that this is like generation and this is distribution. How we connect between them? Well, it's easy, huh? We complete the circuit. Wire to the load, and after that, you complete or you close the loop between the generation and distribution. So this will be the transmission line, for example, as an example. So the question here, how many wires we need? We need 2, right? Which is basically, if we have this over long distance, the generation at far away site than the distribution or the center or the load, we need 2 wires now to connect between them. Okay? What about the three-phase system? What if we have now not only one phase, we have A, B, C. What do you think? How many wires we need?
Is it 4?
Well,
2.
That's it. For each one of them, we will need 2, theoretically. Meaning that, well, you have A, you have B, you have C. Each one of them has 2 terminals here. Each load has 2 terminals here. So you will start to connect, right?
Yes.
So how many wires?
Gonna be 6.
6, but we don't do it with 6. Why?
Because maybe we can use only 2 for all the terminals. As you can see.
let me tell you what's the problem with this arrangement. Although theoretically it's correct because you need to complete the circuit for each phase.
The loss
The
is
issue with this is cost. If we're talking about, for example, generation, okay, if this is a generation, and this is load or distribution, and the distance between them, let's say 300 kilometers. What does that mean to you?
That means we need a wire that has this length.
That's true. It means that with this arrangement, with this theoretical arrangement, you need 6 wires for 300 kilometers.
Which is so long.
And this is cost. Why? Because it is costly actually to build the towers and for the cables and the material, etc. So we don't do this. What we do a couple of things to save in wires. Instead of using 6, we use 4. This is the first stage. How we do this? How we change from 6 to 4? Well, we reduce basically, or we make certain arrangement at the generation side and certain arrangement at the distribution side such that we minimize the number of wires that we use in transmission. What will be this arrangement? Well, the first arrangement is what we call the Y connection. You remember the Y and delta? I think you covered them in 204, if I'm not mistaken. Anyway, the Y connection is basically we connect between the 3 faces in what we call Y connection or star connection, meaning that we connect all the ends together at this point, okay? And we do the same for the load, for example. And that's it. So how many wires do you think we will need now for this arrangement?
Maybe we can see 2.
Well, for each one, this is
Gonna be 1.
2,
So 3.
3. All of them, they are 3 faces, right? A, B, C. But also, once we come here and connect, we need to complete the circuit, because remember, you need to complete always the circuit, right? And then instead of having 3 wires, there is no need, because you are connecting just single point to single point, so 1 wire will be enough. Do you agree?
Yep.
So instead of using 6, we can use now 4. But to make this happen, we need to connect the 3 generators and the generation side and what we call Y connection, and the 3 loads. Sorry, these are loads, huh? The 3 loads at the load side also in Y connection. So now we have only 1 terminal here that we need to connect to the load, 1 terminal here, 1 terminal here, and this will be the negative side or the return path for the whole circuit.
Doctor,
Mm-hmm.
the last wire you drew, you drew. It's not clear why we need it.
Well, it's similar to the wire and single phase circuit. For example, here, if you have single phase, the current will go from here to here, to here, then what? Should come back to the same generator, right?
Yes.
Because you need to complete the circuit. You cannot leave, for example, this open circuit. What will happen if we don't have this wire?
It will be open circuit.
Yeah, so if we don't have this wire here, nothing will actually flow in the whole circuit because it's going to be open circuit. So yes, you need to
I
complete.
see the direction now. Yeah, yes. I see the direction.
Yeah. So this wire here, we need it for the same purpose. You cannot have all the currents going from to the left to the right unless and there is no return wire for the whole circuit. So now, instead of using 6 for the three-phase system, we use only 4. Huge advantage. Not technical advantage. Mainly it's economical and cost advantage. Okay? Any question?
Doctor,
Mm-hmm.
since we reduced the number of wires, is it gonna affect on the size of the wire, the diameter of the wire?
Only this one. The fourth one. Because the amount of current you have here, the amount of current you have here, the amount of current you have here should be the same as before, right?
Yes, and the size will be the same.
The size will be the same. But instead of using one single return wire for each phase, now we are using one for all of them. You
How
get my
about the
point?
cost? Yeah. How about the cost of this new wire? Is it the same if you use the previous one? Because the size has been changed.
Yeah, good point. But let me tell you what, this will be the second reduction. Actually, we don't use this fourth wire. We don't use it. In reality, if you remember even last time when I showed it to you the tower, I said count the 3 wires, right? A, B, C. In practice, we don't use the fourth wire. Why?
Is it grounded?
True, but the reason actually why we don't need it actually is that the current, expected current in this wire is 0. And it is like a magical thing here with the three-phase system or with multi-phase systems. And let me explain to you why. We have current here which is IA. We have current here which is IB. We have current here which is IC. So what should be the current here? KCL. You remember KCL? The current here, IN, will be the summation IA plus IC plus
Will be equal to 0. The summation equal to 0.
that's correct. ما ادري وين راحت طبعا هذه معليش ادري عنها. خلاص راحت. Anyway, the summation which is I in the fourth wire will be IA plus IB plus IC. Yes, we would expect, of course, all the currents, they will be summed up, and this will be the return wire, which is the fourth wire, right? But since the angle here is distributed between them, meaning that this is the angle 0, this is minus 120, this is 120, mathematically, and they have the same magnitude. So if you add all of them, they have the same magnitude. So this is common. 1 0 plus 1 minus 120 plus 1 120. If you do this mathematically, this will be equal to 0, which is a huge advantage here. What we are saying here is that the summation of all the currents all the three phases currents, if the magnitude is the same, and if the angles, or the angle is 120 degrees phase shift, if you add all of the currents, the summation is equal to 0. So do we need the fourth wire here? This is the question. So we said that we have 1, 2, 3, and after that we should have the fourth wire. And we know that this is A, this is B, this is C. Do we need this fourth wire? No. Why? Because theoretically the current is equal to 0. So if you don't expect any current in the wire, why you are actually building a wire in the first place? You get my point?
مو المفروض يكون زي الجراوند دكتور؟
That's correct. This is the solution. You don't build the wire. So this one is gone. No need for the wire. But for protection reasons, because usually in practice, systems, they are not completely balanced. When I say balanced, it means that the magnitude of all the currents not exactly the same. The angles between the phases not exactly 120. So to have, like, for protection reasons, you put this in a ground, you put this in a ground. Why? Still, we expect this current here, IN, to be equal to 0. But if there is any slight, basically, difference between A, B, and C, what will happen to IN? It will not be 0.
It will be more than 0.
It has certain value, but not 0.
But the circuit already open, so
it's not open. You have ground here. Okay, so the ground here will play like virtual fourth wire. It's imaginary. It's there. You don't need it, but it is there. Why it is there? Because you already connected this point to the ground. You connected this point to the ground. Does that mean that the current will go through this? No. No current will go through the 2 points. No current should go through the 2 points because we expect the current to be 0. But if there is any difference between the 3 currents here, and IN here is not 0, at least this current now will go to the ground. So consider this as like exit point for the currents, if they are not, perfectly balanced. So what if we don't have this wire? What will happen? Well, if the 3 currents are not the same, and we don't have this wire,
make a trip.
The currents will come to this point, and the summation of all the 3 currents in this point will not be equal to 0. So there will be return current inside the system itself. So the current, the summation will be circulated in the system.
Wouldn't affect on the fail of the system, Doctor?
It will affect, it will make the system more unbalanced, and the losses will be higher. You get my point?
And yet the system will fail, صح؟ حيصير له يعني.
Eventually, yes. Yeah. Because this will start to circulate inside the system. أنت مو قاعد تطلع من السيستم. This difference to keep the system balanced should be out of the system. And since we don't have 4 wires here, we need this grounded wires for protection reasons. So the system, actually, it's called the 4-wire, 4-wire systems, but only with actual 3 wires. Because the 4th wire is imaginary or virtual wire. So whatever I explained here, for example, if you remember, yes, this one, for example, is A, and this one is B, this one is C. This is what we see. This is what we build in the transmission line. All of them, they go in the same direction. All the currents in these 3 wires should be the same. The phase shift is 120 degrees. But at the end, at the load side or at the generation side, we have either Y or delta. We'll talk about delta now. Either Y connection or delta connection, and you have in the Y connection at the neutral 4th wire, or you are grounding the neutral of the Y connection. Okay? The second connection that we need to talk about before we stop today is the delta. We said that if we connect the 3 sources to a certain point, this is called the Y connection or star connection. We have another connection that we can make for the 3 phases at the generation or at the load side, which is called the delta. This is when we connect the 3 sources in series. This is called delta connection. What's the difference between them? What do you think, guys?
I think in the Y connection, the current is accumulated, but in the delta connection, the voltage.
That's correct. There is a relation between voltages and currents. But from connection point of view, what do you see the difference here?
The junction that was in the Y connections, not the same.
That's the neutral here.
Yes.
Here you have only 3 wires can be connected to the system, right? Here you have actually 3 wires plus 1 virtual, which is this. So for protection reasons, this one you can use the ground, but this one you don't have this option. Okay? So in principle, you have different options for the 3-phase system you can do at the generation or at the load side. At the generation, you can connect the sources to be Y or delta. At the load, you can connect the loads as Y or delta. So we have 4 different combinations: Y, delta, delta, Y, delta, delta, Y. Okay? And these are the 2 connections, as you can see here, the Y and delta connections. They are explained at the generation side, but even at the load side, you can do the same connections. The main issue that we need to deal with here, if we make the Y or delta connection, is that because of the connection, the current, for example, in the source might not be the same as the current in the transmission line. The voltage at the source is not the same as the voltage at the transmission line. That's why now we are classifying all the quantities to be either what we call phase quantity or line quantity. And let me define here what do I mean by phase quantity, for example. The phase is basically the component here. So you see this source here. This is what we call the phase. So if I say, for example, the voltage, the phase voltage, I am talking about the voltage across this element. When I say the phase current, I'm talking about the current of the element or inside this element here. Clear? If I say line current or line voltage, the line current will be the current in the line itself. The line voltage will be the voltage between two lines, for example, between A and B or B and C or A and C. Okay? Again, the line current, the phase current or the phase voltage, they are the current and voltage and the element and the source. So the phase voltage is the voltage across the source itself. The phase current is the current in the source itself. The phase and the line voltage and line current, they are the voltage and currents in the line itself. So the line current is the current in the line. The line voltage is the voltage between two different lines in the transmission line. So this is the phase, this is the line, yes.
For the current, is it the same? The current at the phase?
It is the same. That's exactly, yeah, that's correct. But not necessarily both components, they are the same. For example, yes, for the Y connection, this current is the same as this current, right? Both of them, they are the same.
Yes.
But does this voltage V phase is the same as line voltage?
No.
They will be the same if both of them, they are in parallel. Are they in parallel? I mean, the V phase in parallel with V line and this Y connection? No. V line, you measure the V phase, sorry. You measure the V phase between this point and this point. You measure the V line between this point and this point. So different points, right? So they are not in parallel. What about the delta? Let's start with the voltage. Is the phase voltage the same as the line voltage?
Yes.
Yes. Why? Because the phase voltage, you measure the voltage between this line and this point and this point. For the line voltage, you measure the voltage between this point to this point. So both this is considered to be same point, this is considered to be the same point, so the voltage is the same. What about the currents in the delta connection? Is this current IAB the same as I line?
No, it's different.
No, different.
Because they are not in series, right? You have this, if you apply KCL, you will find that these are both not the same. If you apply KVL, you will find that this line voltage is the same as phase voltage. Here, if you apply KCL at this point, you will find that this current is the same as this current. If you apply KVL here, you will find that this line voltage is not the same as phase voltage. So in summary, for the Y connection, the line current is the same as the phase current, but the line voltage is not the same as the phase voltage. For delta connection, the line voltage is the same as the phase voltage, but the line current is not the same as the phase current. Okay? Is there any relation between the line voltage and the phase voltage? Yes, there is a relation. And we're gonna basically talk a little bit about this relation before we stop today. And this is the Y connection connected to a resistive load. If we apply